We've talked about ideal gases. Now we have to talk about real gases. What we said about an ideal gas from kinetic molecular theory, no attractions between gas particles. When they bump into each other, they just bounce off, no attraction, and the particle volume is negligible, small enough that it doesn't matter. Real gases act much like ideal gases at standard temperature and pressure. Here we can see the molar volume of all these different real gases compared to an ideal gas, 22.41. You see that these are all quite close. In fact, helium nails it, right? They're right on, very close. But there are situations like high pressure and low temperature where things don't go so ideally. At low pressures, like 1 atmosphere, the molar volume of argon, nearly identical. As we increase the pressure, though, what happens is we squeeze these particles closer and closer and closer together, and now the size of the particles begins to have an impact. They begin to be having a significant part of the volume, and that skews the behavior. We find that the actual volume is greater than what the ideal gas law predicts. It's not huge, but it's significant. So here in red is the ideal gas, and here's argon. As we increase the pressure, we see that the volume of this 1 mole of argon is higher than what's predicted by the ideal gas law, because the volume of the particles is becoming important. So what do if you really want to calculate things correctly at high pressures? Well, you modify the equation. You add in some fudge terms. Any question?
So when you shoot the container with the gas in it, does the speed or the velocity of the particles move or increase? Or
That's a good question. So when you compress a gas by shrinking its container, does that cause the particles to move faster, or what happens there? Well, it increases the pressure because the particles are hitting more frequently. If the temperature is the same, the average velocity will be the same. But the pressure is higher because they're hitting the walls more frequently because it's a smaller area. Yeah?
That in and of itself won't change the temperature, like the action of heating it?
It can change the temperature. It kind of depends on what you allow. So, have you ever wondered how your refrigerator makes your food cold? It has to do with a compressor, and you need a gas in there. Same thing for an air conditioner. When you compress a gas and let it expand again, you can have a temperature change. And that's the principle behind air conditioners and refrigerators and freezers. So if you allow the temperature to change, it will. But if you hold the temperature constant, then the pressure will just increase. And it gets kind of complicated because, it's easy enough to keep the amount of gas constant, but then you've got pressure, temperature, and volume, and those can all change, and then things get kind of odd. So 1873, van der Waals modified the ideal gas equation. And so he just added in this term plus NB, because the molecular volume is larger for a real gas. So B is called a van der Waals constant. It's different for every gas. And so you would just have to look that up. And the N here is that number of moles. We also have an effect of intermolecular attractions. At high temperatures where the gases are moving quickly and they run into each other, they have so little time to interact with each other that they don't. But as we get slower and slower and slower, because of low temperatures, now when they run into each other, they're close to each other for longer, and they do begin to have interactions. It's kind of like they're sticky, right? If you run into it real fast, it'll still bounce off, but if you run into it slow, you might stick to it. So at low temperatures, the gas atoms spend more time interacting with each other during their collisions and less time colliding with the walls. And so that makes the actual pressure less than what is predicted. So here we see the wrong graph. That's the effect of particle volume. Dang, I'll have to fix that. So ignore that. So there's another modification to the van der Waals equation for low temperatures, and this is the van der Waals constant A. And so this makes the pressure smaller, and so it's minus A times N over V, the quantity squared. If you combine all of those together, you get this big old mess. Usually we avoid this by just dealing with the gases at temperatures where they act ideally. I want you to know about this. I'm not going to give you any exam questions on this, but just know on the van der Waals equation. You should know what happens to their behavior at low temperature and high pressure. Here are the constants with their units. So what we see for ideal gases and real gases. So if we plot pressure volume over RT, so for 1 mole of gas, that should give us a straight line that's equal to 1. We're graphing against pressure here. What we see for things like helium is that as you increase the pressure, we have an increase in that ratio of PV over RT. That tells us that the most important factor for helium is its molecular volume, the volume of the molecules. For things that go below, like water or even xenon here in this area, that means that the most important thing is the interaction with the different, between the particles. So curve lower than ideal, it means intermolecular attractions are important.